Hello, everyone. Welcome to the first seminar of the semester. I am not the official host. I just wanted to say hello and welcome to everyone, both folks that are joining us again and the large number of new students and postdocs and faculty who are joining this semester. So I'm really excited for the seminar, which has been arranged and scheduled largely by Eric and Paul. I will let you guys talk about what we're doing this semester and the theme, and yeah, so take it away whenever we have a good quorum to get started.
Hosting the Cosmic AI seminar for the semester. This semester, we're going to try to focus a little bit on some observational topics and the connections in with AI there. And to kick us off with this, we have NRAO's own Urvashi Rau, who's joining us from another NRAO location in Socorro, New Mexico. Urvashi has a continuing appointment as a staff scientist at NRAO. She's worn many hats and has several decades of experience with radio interferometry, now getting into some AI stuff as well. And she is currently the NG radar data processing lead for a new radar initiative that NRAO is working on as well. So we're really excited to have Urvashi kick off everything for this semester. Urvashi, you can go ahead and take it away.
Okay, thanks, Ryan. And thanks to the rest of the Cosmic AI group for this opportunity. The picture on the right that you're seeing is how the Cosmic AI Consortium has depicts what we call the astronomy research cycle, right? So it has observation, analysis, and interpretation. What I'm going to try today is to describe what radio interferometry looks like in this context, and hopefully give enough information so that people who are experts on the AI and machine learning side can see where connections can be made. That's at least the goal of this talk. So let's see how we do this. All right, so there's the cycle again, and I would like to split this into three parts. There's the taking of the actual data, which is the observing, the processing, turning it into products like images, and then the interpretation where you end up doing the astrophysics, right? So observing, of course, includes setting up the telescope and scheduling it and making sure it is optimally used, being aware of the environment during which the observations are happening, and sometimes the use of predictive models and being adaptive about your observing choices. So that's the kind of thing that happens at the data taking stage. Processing can be summarized just pictorially as whatever you do to take the raw data to products, which in our case could be images, spectra, time series, and other things. And so there are various stages that we do, which I will talk more about. Then there's interpretation, which is where you take those images and spectra and you extract features from them. You classify them, you recognize them, and infer the astrophysics. And that's where you all of the work on cross-referencing vast databases, getting models that understand links between all of them, and being able to interactively explore all of that comes in. Now, the Cosmic AI has these four pillars that the groups are focusing on. And 3 out of the 4 pillars belong in the box on the right, in the interpretation land. And rightly so, because that is where all of the core astrophysics happens. The pink bar, which is the observable universe, that I think is what I'm trying to split into observing and processing, and that will be the focus of today's talk. So try to go into some depth there to see where ML and AI can apply. I'll try to do this from the perspective of processing, which is just turning raw data into products, and try to focus on what it is we measure, what it is we model and reconstruct, and how we make decisions about things. And as we go through this, try to extract information about the themes listed at the bottom. Basically, how hard or easy are each of these steps? How well constrained are the steps? Where is the guesswork? And hopefully that answering those questions will give us a little more insight into where machine learning and AI techniques might be able to help, and not only in speeding things up, but in actually making better leaps of faith. Okay, so this is what I'm going to try to convey today. So we'll start with what we actually measure and why. Right? So I'm going to start from what we usually describe as the beginning in this case is how does radio interferometric imaging work? First of all, an interferometer is an indirect imaging device. right? We don't directly measure image pixels, but we sample the spatial Fourier transform of the sky brightness that we are trying to image. And the idea is, a spatial Fourier transform can represent any image as a linear combination of sines and cosines. And so the basic principle is if you measure enough sines and cosines and add them up together, you should be able to reconstruct your image. Okay, that's the basic idea. Now, if you look at the picture on the right, it turns out that if you have a pair of detectors that are separated in space, they are sensitive to one spatial frequency. Okay, and it's related to the Young's double slit experiment and these concepts where antennas or locations on the ground or locations in space that are further apart are sensitive to higher spatial frequencies, and antennas or sensors that are closer to each other are sensitive to lower spatial frequency. And so the game now becomes, how do we measure a spatial frequency and what you mean by measuring that, and how do you measure as many of them as possible? So we measure them by sampling the electric fields incident at these two locations. I and J represent two antennas in our case. And we take their complex product and integrate over time and frequency. What we get out is a complex number, which we call V, the observed visibility in this case. It is a complex number, and it represents the amplitude and phase of one of these sine waves. And the wavelength and orientation of these sine waves is given by geometry, literally how far these detectors are apart and their orientation in space. And so just by doing this one measurement, we have all the information we need to construct each one of these sine waves. So then our job is to accumulate them together. We do this in what we call the UV space or K space, which is the spatial frequency domain. We could just make fringe patterns or these sine waves from each of these measurements and add them up, but we're doing the addition in the other domain, which is equivalent. We call this UV space. Other disciplines call it K space, so hopefully that jargon is recognizable to some. The black circles, as shown on the picture on the bottom left, represent the locations at which the complex numbers from, say, the three marked pairs on the picture on the right, where they would fall. And so the black points are where those measurements would be placed on this grid, and the gray points are their complex conjugates. So you can see that the more number of pairs of detectors and antennas we have, the more number of measurements we have on that space. And our goal is to fill it up as much as possible. And once we do that, it's a spatial frequency domain. So all we technically have to do is take an inverse Fourier transform and make an image. Okay, so here are some pictures of what this could look like. The picture on the top left is just a synthetic sky which just has 4 spots. Okay, it's just 4 spots. The picture in the middle is this K space or UV coverage space with where a sample has been measured if you had just 2 antennas. So it's 1 point and its complex conjugate. And the picture on the right is the image formed from such an instrument, which in this case is just 1 sine wave. But as you add antennas, you have more number of pairs, and you can slowly see that just measuring more information on this UV space is able to give you something where you begin to have enough information to see that there are 4 sources there. It's not great yet, but it's there. As a function of time, you can also get more samples because our antennas are located on the Earth and they rotate with respect to the sky. So as seen from the object, the distance between every pair of antennas keeps changing. So as a function of time, you actually get more coverage and you can improve your image. And this is how we do aperture synthesis. Okay. Now, if this is all you've observed, the image on the right is the best that you can get. You can clearly see that there are 4 sources, so there is enough information there to be able to extract the fact that there are those 4 points. But there's all of this stuff around them. And there's a point spread function that is sitting on top of each of these sources, which is related to what we now call the sampling pattern, this big thing in blue that has appeared in the middle. The fact that you have all these artifacts comes from the fact that we have not completely sampled our K space or UV space. Okay? The fact that there are gaps and holes in there is what is causing those artifacts. And so we now have an image reconstruction process where we have to undo the effect of this sampling function. Okay. So it's a bit more than just a super resolution or a denoising exercise. It is filling in missing information in between the measurements. That is the essential problem we're trying to solve here. So let me describe how we do it currently, and I hope this gives enough insight as to where machine learning methods might come in. So let's see how to describe this as a system of equations, right? And don't worry, the level of equations that I have in this entire talk are at the level shown here. There's not too much beyond that. So you have a sky, which is the image, a vector that represents the pixels in an image that you are trying to make an image of. You take its Fourier transform, and then you apply a sampling function to it, add noise, and that's what you measure. Okay. So a couple of pictures just to illustrate this. Here's an example of a galaxy with structure that's a little more complicated than 4 spots, and that's why I wanted to show it here. On the top is the image, true image itself, and at the bottom is its Fourier transform, so what we call the visibility function. The image on the bottom is a thing that is multiplied by our sampling function as part of our instrument, as a part of our measurement process, and that's equivalent to convolving your true image with a point spread function. And so what you get at the end are observed visibilities, which if you were to take just a direct Fourier transform, or a Fourier transform of just those data, you end up with the image on the top left, which is a smooth version of the true thing, but with a lot of artifacts around it. And so reconstruction is all about going all the way back to the top right. We do this through just regularization and optimization. So we minimize the L2 norm. We first find a model. We model the sky in some basis, and we minimize the L2 norm subject to various regularizations and priors and constraints. We solve this iteratively, method of successive approximation, and you end up with an algorithm structure that looks kind of what the loops shown in the picture on the left here. So you start with data on the far left, because our data are just lists of complex numbers. You put them on a grid because you want to take Fourier transforms. So that's the gridding, and then you go there. And then you take an inverse Fourier transform to get your raw image. There is then a jump that has to happen where you make your best guess of what the true image, underlying true image is. And there are several algorithms to do this, but you make a best guess, and you take it back to your data and you keep iterating. This is just standard chi-squared minimization logic. Okay. And so just to depict what this model image might look like, you can slowly improve your approximation of the true sky and keep connecting it back to the data. Now, there are a lot of algorithms that do this. And if you think of what a typical algorithm ingredients might look like, you can see how many different kinds of algorithms can exist. You can choose how to model your sky. Some algorithms pick delta functions, some pick Gaussians, some pick wavelets. Some model the sky in terms of spatial frequency power laws. There are all kinds of things you can do. Then there are priors and constraints. You can say that the image has to be positive. You can say it has to be smooth. You can say all kinds of things. So there's various ways of establishing, biasing your reconstruction. And the reason why you need this biasing is because look at that S, right? That S is your sampling function, which has zeros in it. And if you write it in this form, it becomes pretty clear that your S is a singular matrix, and so no true inverse exists. And that's why we have to do all of this. And that's where the guesswork comes in. You can also pick different optimization strategies. You could either do steepest descent, conjugate gradient, or you can even do an MCMC to just sample everything and figure out which one you like best. And you can make choices of what instrumental corrections to apply. So there's a large variety of algorithms here available. And where some people have tried machine learning and AI approaches are to simply take super resolution and denoising approaches where you train something to jump directly from the top to bottom here for a particular instrument or a particular range of point spread functions, and apply that in this green box. Right. Another approach that some of us are interested in seeing whether it's possible or not, and would love to learn from the ML AI community on this, is it possible to learn a basis set? I mean, The reason why so many algorithms exist is because every new second person picks their new basis set and says this is better than the other ones. But is it possible to actually learn an optimal one, and how does that work? So that's one idea. Now, with all of these algorithms, you can ask the question, do they all give the same answer? No, they don't. So here's an example of just 4 of them. From left to right are different algorithms, and top to bottom are different representations of the same reconstructed model. Okay, let's just leave it at that. There is obviously variability here, right? So now you can, and this is only 4, there are many others. So you can ask the question, which one's right? Technically, they all are, because they all fit the data, and there are an infinite number of images that would fit the data. So now you're down to making guesswork and educated guesses and applying biases to make it look realistic, because you don't actually have all the information you need for a complete measurement. So just to illustrate that is the level of uncertainty that can be present just by choosing different algorithm ingredients. There are some objective ways of quantifying, which is better and all of that, but they're not always, the complete picture. One is a residual image. This is what's left over in your data after you have made the best model you can. And it is simply a measure of how well have you fit the data. It does not tell you whether you have put in sensible things in the areas of your UV space where you don't have measurements. It only tells you that where you do have measurements, how well have you modeled it, which is something. And you would like this to be noise-like. And so if you look at the progression of algorithms here, the one on the right does show that it's able to fit the data a lot better. But it is also the most computationally expensive compared to of these 4. And therefore, most standard pipeline, at least the pipelines that, say the ALMA pipeline, for example, picks the algorithm on the left. And you might wonder why, but it's mainly because that is the fastest. It is the simplest to tune and run predictably. It is also perhaps the most robust. If you give it partially calibrated data or imperfect data, it still does something sensible, whereas some of the other algorithms may fall apart. And so there's a choice here to be made between standardization and something that works 90% of the way on every possible thing you can run it on, versus something that works only on a smaller subset of data, but does an optimal job. So there's an interesting balance to work with here, and depending on use case, people make different choices. Okay, so this is what I'd like to say about image reconstruction. Okay, there's a lot more, but for this talk, let's stop with this. Okay, so let's look at the equation at the top again. I'm going to add one complication to it. So I'm going to add some terms which labeled as G's before this, in front of the sampling function. What are they? They are antenna gains, or they represent antenna gains. So the front-end electronics and the signal path, the way we actually just measure the signals, they modify the signal themselves. And so you can model this as a complex gain, a complex multiplicative gain per antenna. If you look at the picture on the bottom left, you have the incident E fields at 2 locations I and J. Each of those antennas introduce a G. And therefore, when you measure this EI, EJ star, your visibility, the complex number, what you get is also the product of the G's along with it. Now, if you look at any of these equations, it's a product of 2 unknowns. So now what do you do? So we solve this by what we call calibration. And it's a sequence of steps where we first observe a known calibrator source. So a source for which we believe that we know what EI, EJ should be. We observe that source in a time range before and after our target time range. So it's illustrated by the blue bands on either side of the red. We then derive a model of the G's from those data in the blue bands. And this is done as a nonlinear least squares solver, because the expression you're solving is GI times GJ star times visibility. You have the number of unknowns are equal to the number of antennas, and the number of constraints are approximately the square of that. So it's a reasonably well-constrained system. And so you can derive G's in those blue regions. And then you use that, and that's now your model. So now you interpolate across the time range of your target, and you believe that that is the best that you have at that point. And then you divide the target data out by your generated gain values from the model. That's what we do for calibration. Okay. Procedurally, this seems straightforward, But in operations, there are a lot of variants of how you solve these Gs, largely because you don't always have enough signal to noise to do it in just one fell sweep. So you have to do it in stages. And therefore, there are a lot of choices to be made. So accurate gain solutions depend on signal to noise ratio, how fast they are changing with time or frequency, and how well you know your eye, the sky structure, because remember, you need to know that to solve the Gs. So the picture on the left here is a depiction of what the data might look like if you had gain variations that were varying strongly along the time axis and varying slowly along the frequency axis. So you would ask questions of, is there enough signal to noise ratio to calculate the gains independently for every time and frequency? Or do you need to average across time or frequency? There's a balance to be struck. If you average too little, you may not have signal to noise. If you average too much, you may wash out the very signal that you're trying to solve for. So there are choices to be made that are data dependent. So in rather vague terms, some areas where ML or AI might apply is adaptive data dependent choices. At least that's the one thing some of us could think of. And maybe if some predictive calibration. And these are ideas that they're just ideas at this point. All right. So we are done with the gains. Let's add one more complication. So let's add this n at the end of the equation. The superscript there is RFI, which is radio frequency interference. Now, what is this? It's unwanted signals that come in and contaminate our data, which we need to find and remove. And the picture here shows a plot of the spectrum at L-band at the VLA, and all of the spikes are man-made signals that contaminate for us, they contaminate the data. So what do we need to do? We need to find them and deal with them. And I'm being ambiguous about this. So how do we deal with them? We typically run outlier detectors, and then we mask those data. And there are both manual and automated ways of identifying outliers that are in play. Several are heuristics-based. Some of them are signal model-based. Some of them are statistical, which just does statistics-based masking. Now, the picture shown here is a time frequency plane, and the bright, colorful features are all interference. And the actual signal we want is the sort of lightish blue background there. The middle panel shows what an outlier detector might do with, say, default settings. I mean, the simplest possible thing, where it gets the really bright stuff but leaves the weak stuff in. And with a lot of tuning and hand-holding, you can get it to do the thing on the right, where it has found all of the interference and it has masked it well. And you're left with what you think is good data at the end. Now, I'd like to point out one thing, that when we say we mask the data, we're actually throwing it away. Okay, so there's a whole other class of algorithms and ideas to think about of, can you model this interference well enough that you can actually subtract it, not just throw it away, but subtract it and therefore recover the good data underneath. So that's a whole other area of research. There are algorithms that can do this in certain specific situations, but it is never robust and general enough to work in all cases. And so there's a lot of scope in this area for machine learning approaches. And I look forward to seeing what ideas people might have here. But it basically comes down to modeling these RFI signatures well enough to either mask them properly or, even better, to subtract them. And it all comes down to recognizing patterns, maybe doing prediction from past behavior, time ranges where you expect things to happen and expect things to not happen, and so on and so forth. So these are mostly in the idea stages. People have been prototyping ideas, but nothing has made it to, say, production use yet. So there is a lot of scope. Okay, so those were the main building blocks. And if you now look at the full set of equations, in what sequence do we do this? Okay, we start with the raw data. We do a flagging operation, and ideally that will take care of all of that interference. We then do calibration. Ideally, that takes care of all the gains. And then we do our imaging, which hopefully takes care of everything else. And what we are left with is a model of the true sky, which we then turn into products for interpretation. Okay. But in practice, it is not as simple as just 3 steps, because this is a joint system of equations that we are solving. And each of these steps are essentially solving subproblems, but they are not independent of each other. They have cross terms. And so in reality, you're going to have loops and repetitions and all kinds of things. And that typically happens when, say, the interference is weak. So you can't detect it upfront, all of it upfront. If the signal to noise is low, your noise is high, so it's harder to do any of this. Or the sky brightness is complicated enough that you don't get a good enough solutions of the G's in the first go. So you have to do it multiple times and bootstrap as different parts of your model improve. And essentially, you need many steps and repetitions to navigate the error surface of solving, or the chi-squared surface of solving the system of equations on top. Okay. One last complication, you may have additional terms. And I'm illustrating one of them, which is a term that is multiplied to the image before the Fourier transform. And this is another instrumental calibration term, which comes into play when you have high dynamic ranges. It's basically instrumental effects that break all your nice 2D Fourier transform approximations. So yes, everything that I said so far, that it's a two-dimensional Fourier transform approximation, is not exactly true if you want to go into the details and look at really high dynamic range. So now algorithms that assume this 2D approximation are going to become approximate. And so all the more reason why you're going to have more steps and choices to make as to as how you navigate this chi-squared space. All right. So if you put all this together and you think, okay, if somebody is given a raw data set, how do you take it through all the way? How do you navigate the space? This is something that scientists have been doing for many decades now. And what people have learned has been encoded in pipelines. So for example, this is what a typical pipeline flowchart looks like. This is a simplified version of what is the current ALMA pipeline. And if people are interested in the sets of choices and the decision making that happens in full detail, there's a reference over here which I would recommend looking at. So as you can see from the colors, there are repetitions of flagging and calibration steps. And then on the right, it moves to various types of imaging steps. The pink boxes are quality assurance, which typically have more humans looking at plots and logs and making decisions of whether or not to restart and go back in this loop. And those are the dashed blue lines. Okay, so this sequence of operations has been defined by a team of scientists, and over many years they update this model. So you can think of it as a pipeline model of how to navigate this chi-squared space from your raw data to your images, and that is defined by trained humans. Okay? And you have teams of data analysts who, during operations, look at web logs and make the decisions of when to go back and how to implement more loops. Okay, the system works. Okay, the plot on the left here shows, as a function of time on the x-axis, the number of data sets that have successfully run through this pipeline. And if you look at the wedge of dark green that is increasing towards the right, that basically indicates that a larger and larger number and fraction of data sets are running through the pipeline without intervention. So in a sense, the model of the pipeline has improved in completeness and efficiency as a function of time, as the scientists have, as they've seen more data and have updated the model to expand its scope of, to expand the range of data sets that fall in distribution, so to speak. So the output of all of this are archived products. And again, here, I would like to bring up the question of what are the metrics that have driven this sort of development. For the sake of consistency, and for the sake of making sure that interpretation is not confused, there is a push to move to standardized products, which, as I mentioned in the image reconstruction thing, may not always mean the optimal choice for each particular data set, but it certainly makes the analysis a lot more secure, right? But then there's an opportunity here, because is it even possible to do optimal processing for every data set and still have that consistency? So obviously the goal is both. And most of the improvements that are currently ongoing, with the pipeline scientific teams and others, is to make the model generic enough so that you can actually get both. And that's an ongoing effort. So one could look at this 10-year timescale and say, can an automated system learn this much faster? Maybe. But let us not forget the fact that what humans bring to this they are highly trained humans. Okay? They bring in core domain knowledge of how the instrument works, the physics, and all of that. And it's a lot more than just experimenting with options and then learning by experience. So, there's a nice threading the needle to be done here, which can be interesting to think about. Okay, but once you've done this, I'm going to make the connection to the astrophysics. Just one slide of that. You can get to feature identification and extraction. And so this is a picture that should be familiar to this group because it's come from the Cosmic AI slides. It represents a multidimensional image cube from which you can extract information. The information could be single pixels, they could be aggregated summaries, they could be reductions along various axes to produce other products. And this is typically very information rich. So if you look at the spectrum at the bottom, there are a lot of what we call confused lines, which just means that there's such rich chemistry happening in that area that analysis has to be done now carefully. And it is those kind of situations where you really need to understand the uncertainties and error bars from the data processing choices. And this is also one of the reasons why standardized data products is crucial, because you want to be able to do the analysis of something that looks like this consistently. So that's just an example of how to connect the data processing to the interpretation. Okay, how does all of this get affected by large data volumes? The pictures at the bottom are 3 out of a few more next generation instruments that are either being built or under construction. There's the SKA in Australia and Africa, run by, coordinated in Europe. There's the ALMA, run by in Europe and the US, and the proposed NGVLA. There's also the DSA. There are multiple telescopes. But what happens to everything we've discussed when you have a lot of data? First of all, there is more data. And this comes down to why people are building all of these telescopes. You want to have more collecting area so that you are able to beat the noise down a lot more and get much more sensitive observations. You also want better resolution because you want to resolve detail in your images. So that's why people get more data. But what comes for it, obviously, is an increase in computing cost. What also comes with it is if you push down the noise really far, all your instrumental effects are much more easily seen. And this connects to the high dynamic range imaging thing that I mentioned earlier. That if you're working with a lot of noise, you can get away with a lot of approximations. But if you push your noise down, you have to correct for a lot more things. And so you need more complex algorithms, and there are more analysis steps and choices to make, because all of the neat approximations break down. And so as you're navigating that chi-squared surface, you're making smaller, steps. So what do you need for this? You need high performance computing and high throughput computing. But you also should remember that manual intervention in such cases is harder. And so you need more automation all the way end to end. So there is a lot of work currently ongoing on the top right box, which is the HPC and the HTC side, including an ongoing connection between NRAO and TAC, I think, to explore how we can port some of our algorithms and building blocks on HTC systems. The box on the bottom right does not have that much work in it yet. And so that's another opportunity. Okay, so I'd like to, at this point, so that ends the overall description and summary of what all we do. I'd like to move on to giving some idea of where the community is right now in R&D, in applying ML and AI to these problems. I'd like to stress that this is only an illustrative list. It is not exhaustive, partly because there's only so much one can fit on a slide, and partly because we simply don't know the full extent of what people are doing. And so we would greatly appreciate it that if people listening here already know of solutions that exist that in a different class that you don't see mentioned anywhere here, please mention it at the end and let us know, because we'd love to learn. Okay, so let's look at processing first. So these are just a few that we'd like to highlight just to illustrate. There are several algorithms that try to take leaps of faith for what we call the deconvolution step, which is taking the image that has point spread functions and artifacts and guessing what a good model might be. So there's one algorithm that trains this for a specific set of PSFs. There's another one that plugs a denoiser into the larger set of loops. And there are several others with autoencoders and all of that. And I will not attempt to describe that in more detail, but there are references for people who will understand this stuff better. People are trying algorithms for RFI identification, that's those outlier detectors. And so there are a number of experiments there. And there are even people, the last link there are people who are trying to look at different formulations entirely of not exactly looking at visibilities and image, but looking at closure quantities and directly inferring information about source structure through another signal formulation method. So there are ideas out there. On the pipeline side, there are several efforts to identify anomalies in a pipeline so as to ease the work of the humans who are monitoring things. One of them is a Cosmic AI project, and another one has been developed for the VLAS pipeline by the local data analyst team, which is another thing there. There are efforts on auto-tuning parameters of typical finicky parameters of a pipeline, and there's one effort on using reinforcement learning to do so. I'd like to highlight the third one, which we're calling AlphaCal. It's a project that some of us are working on, where we're trying to use reinforcement learning to generate a pipeline model that has all the three steps, flagging, calibration, and imaging, and something that can hopefully learn how to do loops and how to make decisions that are data set dependent. This project is being led by Brian Kirk, shown in the first picture there. He is a PhD student at New Mexico Tech and an NRAO Reber Fellow. And he's working with me on the NRAO side and with Dr. Ramya from the New Mexico Tech Computer Science Department as well. And she has been advising us on the reinforcement learning and the ML and the AI part of this. I also want to point out, just to thank the Cosmic AI Consortium for giving the seed funding award to this project as one of the 8 chosen ones. And we are looking forward to taking this over the next year and seeing how well it does on real data. So fingers crossed. All right, I'll show you some examples on the observing and interpretation side. And these have been compiled by Brian, as he has visited about 3 or 4 different astronomy and AI conferences and workshops over the last several months. So it's been compiled by him. So on the observing side, there are several observatories trying things, scheduling, predictive maintenance, how do you handle alerts and various things. And on the interpretation side, there's a huge body of work. Okay? So I'm not even going to attempt to list it all here. This is where the majority of the astronomy and AI community is working. So there is a lot. I'd just like to highlight 3 tools. So the first is that might be interesting for people to go try out. So the first is from the Polymathic AI group, and they have what they're describing as a foundational model for astrophysics interpretation, starting from data sets that come from or images that come from various telescopes. I think it has been pointed out that they don't yet have radio data. So they're using optical and other wavelength bands. But the fact that they don't yet have radio data there suggests that there's opportunity for involvement and engagement there. And I think there's a group at NRAO already connecting with them on that front. One Astronomy is a Chinese effort where they have put an LLM on top of these databases and provided a bunch of tools. And I believe this is something where you can log in and access and try it out. The last one is an Australian effort where they've taken the image archive from one of the large surveys, the EMU survey, and put an LLM on top of it to make searching more interesting and easier. So that's just highlighting 3 tools there. Okay, now, before I finish, let's remind ourselves that we are not the only people doing indirect imaging. Okay, we have this V is equal to SFI thing. There are other domains also doing the same thing. And domains like medical imaging and synthetic aperture radar have far larger algorithm R&D communities than us. And so can we learn from their ML and AI exploration and take some ideas? And I think the answer is yes. A few of us have interacted with counterparts on the medical imaging side, and just to try to understand, is it close enough that we can learn from them or not? And I believe the answer is yes. So if you look at the pictures here, on the top we have radio astronomy, and the bottom we have MRI. There is K space or UV space and an image. And the way you do your reconstruction, which is inverting a singular matrix, finding a pseudo-inverse of a matrix, and you do this iteratively. We have our picture on top, and a picture shown at last year's magnetic resonance meeting overview talks on classic and AI methods for image recon. They very clearly show that there has been a lot of experimentation by the medical imaging community in putting machine learning and AI in various parts of our reconstruction step. So they've tried a lot. They've tried using AI to jump all the way from raw data to the final product. They've tried putting it in select places, and they now have learned where is the right place to put it. Where do you want to put it if you want speed? Where do you want to put it if you want flexibility and those things? And I think there's a lot we can just take from there. Right? So if people are interested, I would recommend two things to read or listen to. One is a video of a talk that was given now a couple of years ago. I'm sure there are more recent versions of this, but this was from last year. Their conferences literally have summary talks which talk about lessons learned from applying AI, and MR in exactly the kind of problems that we have as well. So they discuss different types of method and where they're useful, where they tend to fail. If anybody's interested, I can provide a video link to this talk. Please contact me later on. Or for people who are at UT Austin, you can probably talk to this person directly. On the analysis and interpretation side, a recent paper came out where they where they obviously done a literature search of AI techniques applied to both biomedical imaging and astronomy and looked at the parallels between them. That's probably worth looking at just to get an idea of the similarities. And I'll warn you, that paper is 75 pages long. Okay, so that's basically all I have. And I'd just like to leave you with one summary slide, which has the same picture again. But it just is to share a sort of vision of what things might look like if AI is fully integrated into this observing system end to end. On the observing side, what you want is you want to customize your observations to your end science goals. It's what humans do right now. But is there anything that can automate that? And get only the data you need, not too much, not too less. And with an awareness of the observing environment. On the processing side, there is a system of equations. There's a system of equations that we are solving, and it has multiple unknowns. And you have to model the sky, the instrument, and the environment all together to get at your image. On the interpretation side, where you're analyzing those images or interpreting them, it's often a good idea to understand uncertainties that come because of all of the previous steps. And there's also opportunity to take your astrophysics modeling and inference closer to the data. In some cases, it may even be possible to bypass the image altogether and model the physics directly from the data once you know how the data and how the signal and the instrument and all of that interact. So I'd like to end there with just this is a big picture which I hope has provided some food for thought for all the people here, and looking forward to questions and engagement. Thanks for your time. I believe there's time for questions. Stella, I think I can see only the hands up here, not the full thing. So Stella.
Yeah, thanks, Urvashi. That was really great and very interesting. So I have a couple of questions, but one of them is about the end-to-end prediction of reconstructing the image using AI ML methods. As you said that there's a lot of choices to be made in going from the source observation to the reconstructed images. And so I'm wondering about the training set.
Mm-hmm.
If you're training such a model, is it trained on just the best choice, and like how is that defined, or is some of that through synthetic source modeling where we can actually verify that the source has been accurately recovered?
Okay, I think it's a mix of both. And this question can be asked also of just how you do any algorithm development. How do you know whether you've got the right answer or not? And synthetic simulations are definitely one thing we choose. But in the end, you're not going to know unless you try it on real data.
Mm-hmm.
And so it does come down to defining the span of your training set. So yeah, there's no easy answer. I think you start with simulations and you try, given your domain knowledge, you simulate as much variation as you think you're going to have, train something on that. and then apply it to data, and then you keep expanding. I'm giving a vague answer because, this hasn't actually been done yet. These are ideas. And when humans do this, they do it through simulations, they do it to trial on real data. For example, the ALMA pipeline has about 150 data sets, which through experience, they have identified as, okay, if something can work well on all of these, we have spanned the space reasonably well. So those are real data. But then if you want to scale from there, you can look at the variation across those data sets and then simulate a lot more and then train something out of that. So they're ideas.
Great, thanks.
We were having some microphone issues before. Can you hear us now?
Yes.
Okay, great. Did anybody locally in the room here have questions? Okay, yeah, Chris, go ahead.
Hey, Urvashi, it's Chris, great talk. Quick question, of course, interested in the RFI term there. And you talked about the difference between sort of masking and subtraction. And I'm curious, like what do we need to know about the RFI signal to do subtraction properly?
Okay.
That we don't know now, or that we need to know.
Okay. So in ideal cases, if you knew where your RFI source was, and if it was bright enough in a large enough baselines to actually do calibration and imaging and things, you could actually model the RFI as though it were another source in the sky. It may be moving with time, with space, moving in position with time, but you could send it through the exact same equations that we do for a sky source and model it that way and then subtract it out. That is an option. So there are algorithms that would benefit, and there are algorithms that people have done R&D and proven that if you know the location, you can do this. But then there's also the complication that the correlation process itself damps down the signal from such sources in different ways across baselines. So it strictly doesn't follow our system of equations. And so when your RFI is partially modelable through math, but partially random, that's where you run into problems. That's when it becomes hard to model and subtract. That's at least how I would describe that. And that may be a case where you then resort to modeling patterns and subtracting it out. But that's
okay. Thanks. That's great. Yeah. Unfortunately, for satellites, they're both bright, and we know right where they are. So those two parts are,
which is good.
We can deal. Yeah, that is good.
Good thing. Yes, which is a good
Right.
thing. Exactly. And yes, definitely.
Thanks.
Brian?
Yeah, so thanks, Urvashi. That was a wonderful talk and overview. I was curious for your take on the kind of what the MRI community has learned from trying these things, if you have a sort of a short take.
Okay. Okay, if I were to summarize that in a couple of sentences, it's if you have a restricted range of use cases, they have found really nice ways of automating things end to end. Like in an MRI machine, you sometimes have very specific types of measurements you want to do, and everybody's head looks the same enough that you can, make similar choices. For example, you can make similar choices on how to take the data, how to process them, and then how you interpret. And so they've had some success at making big leaps there through a machine learning, network that has been trained end to end. But then it works well only within distribution. And so if you have a use case that has a restricted, span, then people have been able to use it very successfully to go through all of these steps. At least that's the impression that I got. I mean, of course, there are details, but that's one thing. But when it comes to flexibility, these don't work because you're most of the time out of distribution, and it's very easy to hallucinate and make wrong assessments. And there are several examples that they showed of that as well. But to handle that, they have also tried to understand where it is most important to put the ML and AI. Put it only where there is already guesswork. For example, you don't need AI to learn a Fourier transform. You can encode that in directly. Whereas if you're trying to figure, okay, how do I best model the sky? What's the best latent space to describe that in, for example? That may be an area. So I think all we can take from them is just this, that it sounds obvious when you sort of say it at this high level, but when you're problem space is restricted, end-to-end solutions. They have been able to take all the way to production, and actual, in operations, which is impressive. And where you need flexibility, you have to be smart about where exactly you put it. That's basically it. But one thing that I found fascinating is that that community is so large that they have essentially done an MCMC on the algorithm space. So they have done the exploration, and there's lessons to learn from there. And maybe there's something we can just leapfrog and not repeat that entire thing ourselves. So that's that.
Great. Very interesting. Thanks.
I think there are two questions. I think there are two questions on the Zoom, and there's a question in the chat as well.
William, I think I saw your hand up first.
Yeah, so I might be the two questions in the Q&A, but one of the questions I had is when you're doing your Fourier transform, are you doing internally to your software, your program here, is it just a direct DFT, or are you using specialized transforms that are optimized for each use, or is that all kind of wrapped in your basis function?
Okay, it's a standardized FFT that we apply, and we go to great pains to do processing both before and after, such that a two-dimensional FFT approximation is good enough. So that's a good question you asked. In its full form, this is not actually a two-dimensional Fourier transform. It's a three-dimensional transform. And we do pre-processing and corrections to parts of the equation to make it look 2D so that we can use efficient FFTW implementations to get the processing to happen in finite time. So yeah, that's the answer. So we use the standard 2D thing, but we do other stuff for the specialized math. That's a bad answer, but yeah.
Thank you.
Christina?
Hi, Urvashi. Thanks for the really interesting talk. I was just curious if you have any advice for people who want to get started, using some of these tools. Some of them are quite computationally expensive. It'd be great to have some pointers on where to direct students to go to find, good computing resources where they could play with like a large database of VLA data sets, for instance, and try out some different, some of the different algorithms that you've shown us.
Okay. I think one of the first steps could be simulating data just to understand how the process works in a controlled environment. And that you can then choose how big or small you want them to be. So choose them to be small and learn on that. We have software that we use for data processing that can be run for each of these individual steps. And there are other groups also putting together libraries where it is a little more easier to pry the pieces apart. And so, if people are interested, you can contact us and other collaborators for how to access those libraries. But that would be my very basic recommendation, that if you're starting from scratch, a simulation is a good way to learn how the entire process works. Run any of the existing software packages on that to learn, the nuances, and then take a few data sets. Do it by hand first. Do it by hand so that you get a basic understanding of the nuances and the kinds of decisions. And then and then see what you can do with it. But that would be my recommendation there. That helps.
Well, there are 3 questions in the chat, and if you're in the room, can you please ask them?
Or if you're on Zoom, just come online and ask. I'm looking at the chat now.
So I'll speak up. Just a question. Do you know over time, the patterns fall out of, let's just pick on Wi-Fi or some other RFI. Basically, do you see periodic patterns in human behavior for this RFI interference? Have we gotten that far? Is AI trying to classify that? Or is, that just kind of a wishful thinking?
Okay, I don't think that's wishful thinking. I think the human beings looking at RFI and dealing with them every day, the operators and the data analysts and various people, and including groups who are working with other companies who are producing RFI and to try to engage with them, I think we do see patterns and we do believe that it is predictable enough, but we don't yet have any AI solutions that have figured that out for themselves. So that's why I think there is scope. Is that I think, Chris Dupree, if you're in the room, if you want to say, if there's anything more you'd like to add on that particular point of how much is knowable a priori, that would be, maybe people would be interested.
Yeah, I mean, there's the stuff that we can sort of find by watching for a while, and there's the stuff that we can sort of set up in the way we hope. So you may have seen the news that, for example, recently we're working with the Green Bank Elementary Middle School so that they can use 2.4 gigahertz Wi-Fi in the school. We have an on and off time for that. So that is predictable by design from that particular RFI source. But mostly, yeah, we're having to build up databases. But the good news there is we're moving towards the ability to view all of our RFI data sets from all of our sites with the interactive RFI GUI that Dawn Pattison has developed, Dawn and Aaron Lawson. So we have good input on that, and that'll serve up data from all of our VLA RFI scans, GBT RFI scans. So we're getting to the point where really we have these RFI scans as a database that can be searched for these types of patterns.
Thank you both.
I want to ask a quick question of this group along those lines. So, you know, they have the various data challenges, AI data challenges that have collected tons of data that anybody can go and group. This is the only radio astronomy AI funded from NSF, right? It's one of the outputs to create a big library of radio astronomy. I don't know what would be visibility, calibrated visibilities and images or something that then could be used by other people for data challenges. Is that in scope for?
I mean, I think it's definitely in scope in other domains as well outside of radio, but I'm just going to use this as an opportunity to real quick to read off from the chat. There was a related question. Is there a large data set about how step-by-step the raw data is processed and how the decision was made? So for example, AI agents can learn from these previous human decisions. So maybe Urvashi could speak a little bit about that from like what Brian's been looking at.
Okay, so there are a whole host of data sets, for example, the ALMA test data set ensemble. And there are archived products that have a history of what all was done to produce those products. When the pipeline is run, a history is saved. So in principle, yes, that kind of information does exist. It has to be mined from the NRAO and ALMA archives. Why those decisions were made, it's I don't think has been documented as clearly, but the ALMA pipeline, for example, has wonderful documentation of the flow chart, and so you know and all of it follows that, so you could derive that information. For the work that we're doing with Brian Kirk, it's more learning from experience, and so there we are actively choosing to not use any prior information of how exactly a sequence has been done, but we are trying to explore how much can be learned just by experimentation. And so that it's a slightly different use case there. There are a couple of other questions in the chat. Shall I go through them? Do we have time? I'll take the last one. So Ilsang has a question of, ultimately, do you think that the full forward modeling is possible and it's the way to go ultimately? No idea. Okay, this is just an idea because, okay, this is just an option because there are people who have done this for specific use cases in the past. There are experiments where people have tried to model the physics directly from the visibilities and not even gone to the image. Whether that's possible for every possible thing, every possible use case is unclear. But given the kind of leaps that ML and AI applications seem to be able to take, it's a question to ask, like how much is possible? And I'm hoping that people on this call and, you know, as part of this consortium, there'll be more people who know how those things work much better than us, who will be able to eventually answer that question for us. So that's the hope. Right. Right. Thanks everyone for your time today, and I hope this has given food for thought. So looking forward to conversations. And thanks Pratik and others for setting up as well.